All right, folks. So, as I said, I wanted to start off the screencast talking a little bit about the concept of Dalton's law, or the law of partial pressures. And as I said in class, in Dalton's law, with a mixture of gases, each gas exerts its pressure on the walls of the container as if it were alone in that same container. So let's go ahead and make some drawings here to explain what it is that I'm talking about. Okay, so I want you to imagine this situation where I have two manometers and the B side is open to the atmosphere, and what this is doing is measuring the pressure of a volume of gas inside of the container of our manometer. And you can see here that I have the conditions are the same. We have it's at 25 degrees. We have a certain amount of moles of the O2, and most importantly, we can see that these things have different pressures associated with them. So in the case of oxygen, we have 12.4 kilopascals of pressure inside that container, whereas in the case of the water vapor, we have only 2.7 kilopascals. So when they're by themselves, this is what you would get for a measurement. But if we were to then combine the same amount of oxygen and the same amount of water vapor into the same manometer, all we'd need to do to figure out the total pressure of the entire system is to simply add these two things together. So in fact, if you scooch over here, this is kind of like one of those cooking shows here. If this were the case where you can see now I have both oxygen and water inside of this manometer together, then I would have the 0.0050 moles of oxygen plus the 0.0011 moles of water vapor. This would still be in 1 liter at 25 degrees C. And if we take 12.4, add that to 2.7, we get 15.1 kilopascals. And that is exactly how much pressure would be exerted on the container. Just adding together those things. So it's a pretty simple law here. But what it really does mean is that you can add up all what are called the partial pressures of each component of the gas inside of this container, and that would give you the total pressure associated with both gases, or how many gases there are in that system. All right, so there's Dalton's law. So now what I want us to do is to not take Dalton's law. That's actually sort of a separate thing. What I want to do is take the three laws before Dalton's law, Avogadro's, Boyle's, and Charles, and see if there's a way we can combine these things to make one universal law, an ideal gas law, that would be able to explain all the behaviors of gas associated with those three equations together. So let's go back and take a look at these things. We have Avogadro's. Oops, hold on. And if you recall with Avogadro's law, what that does is it relates the pressure and the volume, I'm sorry, the amount of gas that you have associated with that pressure. So in your notes, you'll recall that as you increase the number of particles, then that's going to also increase the volume. But one thing I want you to keep in mind here is if you have it in a fixed volume container. So let's imagine this. I have whoa, that was weird. We have two containers, and they are the same size container. So I'm just going to go ahead and replicate this right here. Same exact size container here. And I seal this thing off so that the container is now sealed and it can't leak. But in the first container, which is, say, a 1 liter container, we'll say that both of these are 1 liter, this one I put in a whole bunch of gas particles. Okay. And in this one, I only put very few gas particles. Now, don't forget that Avogadro's law, the way that we set it up, we talked about how equal volumes of gases at the same temperature and pressure have equal numbers of particles. But now what if I just mess with the particles and I say, we're going to have the same temperature, but I'm going to remove a whole bunch of particles from situation A relative to situation B. Which one is going to have the higher pressure? I hope you would see that the one that has the higher pressure would be this one. don't forget, with the kinetic molecular theory, we have a lot more particles banging against the inside of the walls of that container, so they're going to exert a much greater pressure. And if that's the case, then if I were to make a graph that showed this, before we showed how volume and the number of particles, it increases like this. Well, we could actually do the same thing. Instead of having volume, however, I could get rid of the V there and instead put in pressure and still have that exact same relationship, right? So I have a fixed volume now, and if I have a fixed volume, as you increase the number of particles, the pressure would also increase. So what does that mean? It means, in the same way that we said that the volume was directly proportional to the number of particles, now we can say that pressure is also directly proportional to the number of particles, or P, right, is directly proportional to N, which is the number of moles of gas. So let's take that home. Then let's address Boyle's law once again. And with Boyle's law, if you recall, that's the one where if you are at a constant temperature, then the pressure and the volume of a gas are inversely proportional to one another. So again, if we go back to the graph to remind you of what's happening here, at a very low volume, you would have a relatively high pressure. So that would have you up here somewhere, right? Again, we have a fixed amount of number of moles of gas here. So if then I were to take that same number of moles of gas, but I increase the volume of the container tremendously, in other words, I pulled the syringe out a little bit, then I would actually have a much higher volume, and as a result of that, the pressure would decline. So this is pressure, this is volume over here, and oh, that was a terrible job of doing that. Let me connect them like this. So we can see how with Boyle's law, that pressure is inversely proportional to the volume. So that means we have P is inversely proportional. So then I have to do 1 over V for that one. And then we go to Charles's law. Let me go to a new page here. And with Charles's law, if you recall what we talked about in class here, that's the one that connects the temperature to either pressure or volume. Okay, so Charles's law. And in this regard, if we were to graph the same sort of thing, let's just choose volume this time, and we have temp and K over here. And if you keep a fixed amount of gas again, a fixed number of moles of gas here, at a low temperature, it's going to have a very low volume. At a medium temperature, it's going to be a little higher. At a little higher temperature, it's going to even be a higher volume. Okay, so it increases in size, just like if we took a balloon and we put it from the cold outside, if you were to bring it inside, it would increase in volume because the balloon is made out of rubber and it's a flexible volume. And if we did the same thing, but this time instead of having a flexible volume, one that would change, we put it into, say, a glass container that couldn't change in size, and we do the exact same thing. We bring it out, and or we bring it inside after it's been outside. Then at a low temperature, we're going to have a relatively low pressure inside that fixed volume container, whereas at a high temperature, the molecules are going to be flying around, smacking into the side of the container at a higher rate of speed, and as a result, that will increase the pressure. And so for this dude, if we're looking at the relationship between the pressure and the temperature, then we would say it's the same thing as what we saw with Avogadro's law. Pressure is directly proportional to temperature, and of course we can say that also volume is directly proportional to temperature as well, right? So if we take these two things, in fact, I'm going to get rid of that bracket there because we don't need to say that. It's definitely the case where volume, in the first case up here, right, is directly proportional to temperature. So let's take all those things together, all four pieces together. We have pressure that is directly proportional right here to the number of moles. We have pressure which is inversely proportional to the volume. we have pressure, which is directly proportional to the temperature, right? And we have here that volume is also directly proportional to temperature. Now, if that's the case, then we can put P over on one side of our equation and say that it's directly proportional to the number of moles, it's directly proportional to the temperature, but it's inversely proportional to the volume, right? Okay, so if that's the case, now if we want to get rid of this directly proportional piece and make it equal, we could do that, but we need to put in a special constant of proportionality that would make it equal. Now, if you don't understand that, don't worry too much about it. Just know that I need to put into this some sort of constant if I want to make it perfectly equal. So I put in a p, and now if I want to have an equal sign, I'm going to put in my constant of proportionality here, multiply n times t, and put that over v. And if I rearrange things a little bit, let's say I want to have no division here, I just want to have it all multiplication, then I'm going to take my volume and I'm going to multiply both sides by v. So then I go P times V equals N, the number of moles, R, our constant of proportionality, and T. Now this right here, folks, is our ideal gas law. And the beauty of this is that we can then use this beautiful ideal gas law to solve a whole bunch of ideal gas law problems, which is exactly what we're going to be doing tomorrow in class. So get ready for it. By the way, there's one last thing I wanted to tell you. Today in class, I gave you guys the answer to letter B or number 2 for the manometer problem. And I gave you the wrong answer. It was leave it to Maya Benson to actually come up with the right answer. I had made some naughty rounding errors on it. So the real answer for number 2 that you're going to want to change now is 790 millimeters of mercury. Okay, so this is again for question number 2 on the work that we did today in class. Bye.